So looking at page 80, we're talking about whether or not a series is absolutely or conditionally convergent. All right, so I chucked in the definitions involving the alternating series test. So and just as a reference piece. So the directions for the problem say determine whether the given alternating series converge or diverge. If it converges, determine whether it's absolutely or conditionally convergent. All right, so let's start off with whether or not they converge. So first off, we need to verify that they are decreasing in nature. So, just kind of refresh our memories here. All right, they converge if both of the conditions are satisfied. The a sub n limit has to go to 0, and it has to be a decreasing sequence. All right, so let's focus on the decreasing nature of it first. A sub n is 1 over the square root of n for n greater than or equal to 1. So that would be 1 over root 1, 1 over root 2, 1 over root 3, and so on. This is decreasing. All right, the limit as n approaches infinity of a sub n is going to 0, right, for whatever rules you prefer to use, whether it's the horizontal asymptote or whether you get into L'Hopital's rule. Either way, or a graphical approach. Either way, we're going to say, and it is alternating series because it's negative 1 to the nth power. So what we would say is the sum from n equals 1 to infinity of negative 1 to the nth over the root of n converges by the alternating series test. All right, so now it's a question of whether or not it's absolutely convergent. All right, so we know it's convergent, so we're going to attempt to show that it's absolutely convergent, and if that fails, then it must be conditionally convergent. All right, so let's find the absolute value of the a sub n, because we tend to overuse a sub n here. So for absolute convergence, what we're looking at is the sum from n equals 1 to infinity. If we find the absolute value, we're just dropping the part that makes it alternating. All right, so this becomes 1 over the square root of n. All right, so this is the same as saying the sum from n equals 1 to infinity of 1 over n to the 1/2. And so it's really just a question of, all right, well, what does this follow in terms of a rule? This is a p-series situation, all right? So it's just a question of under what circumstances a p-series will converge or diverge, all right? So we have a p-series with p between, I'm just going to zoom in, 0 and 1 inclusive. Therefore, the sum from n equals 1 to infinity of 1 over the square root of n diverges. So therefore, the given alternating series is conditionally convergent. Poor quality convergent, so let me write that with a little less chicken scratch. All right, so that's one, or the first problem. So the second one, same general idea and setup. All right, so let us steal as much work as possible I tend to do this and then realize that I have to erase most of it, but we'll see. All right, so this is 1 over 3 to the nth. All right, so that's 1 over 3 to the first, 3 to the second, 3 to the third. All right, so the limit does appear to be approaching 0, the limit of the sequence. All right, so by the alternating series test, we can say that, so -1 to the n plus 1 over 3 to the nth is going to converge by the alternating series test. So that's great. All right, so now we're going to strip away the part that makes it alternating. We're going to find the absolute value of that, which is going to give us 1 over 3 to the nth. All right, now I got to be thinking about what that really translates to. That has the look of something geometric in nature. So I'm going to start a quick expansion of this. So we kind of already did it, but I'm going to do it again. 1 over 3 to the first, 1 over 3 to the second, 1 over 3 to the third, and so on, all added together. All right. So when we start thinking about the proper form of a geometric series, what we want to do is we want to state the starting value, which would be 1/3, and the common ratio, which would be 1/3. All right. The problem is what we'd be dealing with, and so we kind of start off with that. Common ratio meaning the value that you multiply each term of the series to get to the next term of the series. If I make this to the nth power, then our first entry would be 1/3 times 1/3, all right, to the first power, which is going to give us 1/9, which is going to give us our second term. All right. So if I really want this to bear out the proper way without having to adjust the bottom value in my sequence, what I would do is make my initial value a 1. So then I'd be looking at 1 times 1/3 to the first plus 1 times 1/3 to the second, and so on. And so that would get us where we need to go. All right. But that's kind of neither here nor there what the initial value is. Once you identify it as a geometric series, we know that we can determine that this is convergent. So the sum from n equals 1 to infinity of 1 over 3 to the nth converges by the geometric series test. And that's because the R value is between 0 and 1. All right, so we have that accounted for. Therefore, our initial series, copy, paste, is absolutely convergent. And there you go.